All right, friends, welcome back. In this video, I'd like to go ahead and start Chapter 5, and we're going to take a look at Section 5.1, which is going to discuss exponential functions and their graphs. You can see that as we go through the rest of Chapter 5, we're going to be giving you a reintroduction to the world of exponential functions and also logarithmic functions. And so, again, in this video, we're going to take a look at exponential functions only, but in the next video after this, we'll take a look at your logarithms. So an exponential function is what? So this is a function machine that if we turn it on and feed it an input, it's going to take that input and make it an exponent on some number a, okay? And that's why we call it an exponential function, is because your input is treated as an exponent, okay? Now this base number a right here, we do call that the base. And in order for us to have something interesting to study, we have some restrictions on this base number a. So first of all, we can only have that base number a being a positive number. It has to be greater than 0. We run into trouble if we let a be a negative number. We actually don't get a continuous function in that case. But we also don't want a to be 1, because then 1 to any power is just going to result in 1, and that's just going to create a horizontal line in the plane if we were to graph that, and that's not very interesting. So a couple of restrictions on a, just so that we have these nice graphs down here for exponential functions, okay? And so see here that these characteristic shapes kind of swoop up and grow and grow and grow and grow, or maybe kind of swoop down and decrease and decrease. But one common thing that you'll find in basically all parent functions for exponentials is that they are all going to pass through this point right here. So this point with coordinates 0, 1. And the reason for that is because if you ever have a number with an exponent of 0, the result is always 1. Okay, so if your input is 0, the output is always going to be 1. So that fact is maintained as we look at the graphs of those. And what I want to do here is just kind of present to you a couple of the different transformations for exponential functions. These are the same exact transformations that we've talked about for other types of functions here. So that's why I've gone ahead and filled in the notes in this slide, just so we can talk about these and then move on, right? So if we take a look at this graph up here, that's f of x is equal to 3 to the power of x. Then if we go into the inside and put a negative on the input, then that's going to, of course, create that classic reflection over the y-axis that we talked about with other functions. And you can see that that's graphed there in red for g of x. That's f of negative x there. Okay, you can see that that is a reflection over the y-axis. If we instead put that negative on the output, then that, of course, is going to correspond to a reflection over the x-axis there. So we will be reflecting down, and that's what's represented there in green. Okay, so again, anytime you have a negative on the input or the output, that's going to create a reflection over the y-axis and the x-axis respectively. If we go ahead and add a number or subtract a number away from our output, then of course that classically will shift us up or down that number of units. So if it ever says plus a number, like here it says plus 2, we know that we're going to be shifting up that many units, up 2 units. And you can see that that's signified. My parent function is there in blue. That's f of x is equal to 3 to the power of x. And then g of x is defined to be just our output from f, but also plus a 2, and that's going to, of course, shift us up. H is defined to be the function f's output, but subtract away a 2, and of course that's going to shift us down. Now you see these dotted lines here, and what these are horizontal asymptotes, because the graph of the exponential function is going to always have that horizontal asymptote there. And the reason being is if you look at the one here in blue, again, this was defined to be f of x is equal to 3 to the power of x. There's not a single x input that I can plug in here for x that's going to make us reach down into negative territory, and there's also not a single exponent that I could put on a 3 that's going to make the result equal 0 either. So we are going to get very, very, very close to 0, but we're never going to touch it or cross it. So we have that horizontal asymptote there, and again, that's going to come along for the ride anytime we start to shift our graph up or down. We could also shift our graph left or right, and so in these cases you'll find that we have a number plus the input or a number minus away from the input, okay? And of course the interpretation goes, if it says the input plus a number, the interpretation there is that we're subtracting away something that's negative, so we're going to go in the negative direction in which we shift, which is going to be to the left. And then similarly down here, if it says x minus the number 1, then the number that we're subtracting away is going to be a positive in that context, and in that case we're going to shift in the positive direction here. And so there's all 3 of your graphs. Your original parent function in blue shifted to the left for red, and then shifted to the right for green. Okay, and so I'm just going to go ahead and plug this up here as well, just because we've done similar problems to this before. So if you want to pause the screen and kind of read through what you're looking at here, I think that would be a good exercise for you to go through. But here it just says in the directions, use the graph of f to describe the transformation that yields the graph of g. Okay, so we'll just kind of go one by one here. So if f of x is originally equal to 7 to the power of x, and g of x is basically that exact same function, but we tack on a 3, remember that's going to shift us up 3 units on the graph. Okay. Similarly here, if our original function f of x is 4 to the power of x, and we change that by introducing a plus 5 to the input, then of course that's going to go ahead and shift us to the left that many units on the graph. Okay, so again, just kind of knowing whether you're adding a number to the output or adding it to the input, it's going to shift you in a particular way. So here in the third example, if I have f of x is equal to 0.8 to the power of x, then if we go ahead and introduce a negative out front on the output and then go inside to the input and take away a 2, then that's going to create these transformations here. So we're going to shift the graph of f of x to the right 2 units because of that minus 2, and then we're going to reflect over the x-axis because of that negative that's out front on the output. For the fourth example here, we have f of x is equal to 2 to the power of x, and of course if we go ahead and change the function formula in this way by putting a negative inside on that input and then going to the outside and doing a minus 9 away from the output, then we of course create these transformations here. So we're going to shift the graph down 9 units because of that minus 9, and then we're going to reflect over the y-axis because of that negative on the input. Okay, so those are just basically the same transformations that we've seen for other types of functions, but this is what they would look like for exponentials. Now, it turns out that when you study exponentials, there is a very, very important number in the world of exponential functions that we need to be aware of, and it's something that we call Euler's number. Okay, Euler was a Swiss mathematician. You can Google him. His name was Leonhard Euler, and he is widely considered to be one of the greatest mathematicians of all time. Just the number of sheer results tied to his name is actually kind of mind-blowing. There are thousands of results that are named after this guy. That's how big of a deal he was. But this number, 2.71828, etc., 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 we honor Euler today by calling that number the number E, and that's after Euler's name. And so E is going to be something that we're going to kind of develop later on here, and it's actually programmed into your calculator ready to go as I'm demonstrating here. So if I ever give you an example where it says use a calculator to evaluate f of x is equal to e to the x to 3 decimal places, we have all these different inputs like -1, 0.25, and 3/2. We can go ahead and plug those into the calculator by following the sequence of buttons that you see over here on the right-hand side. So in the calculator, in the TI-84, all you have to do is press second and then your LN button, and that will give you e to the power of something. To where you're going to be able to do these examples, and that's how I punch them in to see the screenshot right here. If you ever are doing a calculation where you just want the straight up number e but without an exponent, or in other words with an automatic exponent of 1, let's say, then you just have to go ahead and press second and then the division sign button, and that'll pull up your classic E, okay? But you can see here that these decimal approximations turn out to be what they are here on the screenshot, and so, yeah, let's go ahead and move on and talk about one of the more practical applications for exponential functions, which is your compound interest, of course. And so if you ever apply for any sort of thing where you're going to have to take a loan out, like student loans for college, or maybe buying a house someday, getting a mortgage, there might be interest associated with that. And so the way they calculate that in the discrete sense, where you compound a discrete number of times or a finite number of times per year, you're going to be using this formula right here, okay? And so in this formula, you're going to be putting in the principal amount. That's why I use a capital P for principal, or in other words, just the amount of money that you start with. And then throughout the problem, you see that we have some other variables here. So R stands for the interest rate. Typically, that's going to be something that's going to be given to you as a percent. We're just going to need to convert that to a decimal before we continue on doing the calculation. And of course, that's the number of times per year that you're compounding your interest. So that's the number of times per year that you're taking a certain percentage of your original and adding it on to the total to create your new balance, right? So that number N is going to be right here. We're taking the rate divided by the number of times we compound, and it also is going to show up in the exponent of this formula. So again, just keep in mind how many times a year you compound, that's going to be the number N. And then T is the number of years that we give our original principal amount to grow. Okay, so t specifically is in years. This formula was derived so that t would be in years. So we just need to kind of keep that in mind, right? Now, I want to go ahead and do an experiment here. Okay, so let's just say that you are opening up a bank account and your original principal amount is just let's say that's $1. Okay, you're going to put $1 into an account just to keep things simple. And then you're going to apply this formula where you're going to take 1 plus the interest rate. And let's just say for the purpose of this example that we give you the best interest rate possible, right? Like how about a 100% interest rate, okay? Well, as a decimal, we're not going to put 100 there for R. We're going to write that as a decimal over 100, and that's actually just going to simply be the number 1. So number 1 for R, the rate, that is representing 100% interest rate. And then let's just go ahead and keep the number of times we compound a year general, just because I want to kind of study what's going to happen here in a moment. And let's just say we give ourselves 1 year to go ahead and grow this principal amount. So n times 1 in that exponent, that's just going to turn out to be n. What I want to do is I want to study what happens when n gets bigger. Okay, so the number of times you compound in a year, what if that gets bigger and bigger and bigger and bigger? What would we expect that $1 amount to turn into? Well, I've actually got that ready to go over here, and you'll notice that in the calculator I've just gone ahead and plugged in a larger number for n as I keep going. So this makes sense too, because if I just compound 1 time per year, then the $1 that I started with would grow by 100% by the end of the year, and then that would be another dollar tacked on top of it, so that would be $2, okay? But you notice here that as the number of times I compound in a year gets bigger and bigger and bigger, my dollar amount is getting bigger, okay? So we can kind of see that it's going from $2 to $2.59 to $2.70 here. As the number of times I compound gets bigger and bigger and bigger, we are getting a bigger dollar amount. But if you look closely at these numbers, you might just start to notice a pattern that these numbers are getting bigger, but not by very much. We're actually kind of getting closer and closer and closer to a certain value here, right? And so as we keep compounding and we keep letting the number of times we compound get bigger and bigger and bigger, what we're going to see here is that our dollar amount is going to approach this number E that we talked about before. And this is actually the definition of E, okay? So to use some sophisticated math notation here, it would be that formula, right? It would be that principal amount of 1 times 1 plus 1 over n to the power of n. What we would say here, and this is some calculus notation, but we would say here as n gets bigger and bigger and bigger, or in other words, as n approaches infinity, we would say the limit of this expression is actually going to be equal to that number E. So that's actually the definition of E, is it's the number that we approach as n gets bigger and bigger and bigger and bigger. And again, this has wide-reaching applications in really any sort of real-world model where something is growing at a rapid rate. So that's why the number E is so important. So for example, if we let the number of times we compound in a year be infinite, right, we have a continuous compounding situation, then that's going to mean that that Euler number, E, is going to show up in this formula, okay? So it's going to be the principal amount times E to the power of your interest rate times time, okay? So let's actually go ahead and apply that here. So in example 3, it says we have $11,000 is invested at an annual interest rate of 6%. What we need to do is find the balance after 7 years if it's compounded in each one of these 3 situations, okay? So let's go ahead and say that our interest is going to be compounded quarterly, okay? Well, you think about what a quarter is, right? That's 1/4 of something, okay? And so that's going to mean that we're going to take our year and chop it up into 4 equal parts, and then we're going to compound our interest at the end of each of those parts. So when quarterly is the number of times we're compounding, that is going to be 4 throughout the year. So if we're setting this up, we're just going to go ahead and start over with our compounded interest rate formula. So, or not interest rate formula, but yeah, anyway, whatever, you get what I'm saying. So we're just going to plug in our stuff, right? So we have $11,000 times 1 plus the interest rate over the number of times we compound. Now, just remember that the interest rate is typically going to be given to you as a percent. We just need to go ahead and convert that to a decimal, okay? So if you have 6% here, remember that percent means out of 100. So 6 out of 100, if you were to take 6 divided by 100, that would be 0.06, and that is what we're going to use for our interest rate here. So 0.06 represents 6%, and we are compounding quarterly, so n is 4. And then in the exponent, we're going to do 4 times the number of years we're giving this amount of money to grow, which of course is 7, okay? And I will go ahead and reveal to you a little bit later on what that actually turns out to be, but I just wanted to go ahead and set it up here with you, okay? Now, whenever we're compounding monthly, then that means once a month, and of course there are 12 months in the year, so that would mean that n is equal to 12. So setting this up, we would see that that would be $11,000 that we started with times 1 plus the interest rate divided by the number of times you compound. all raised to the power of the number of times you compound times the number of years you're giving this to grow, which is, of course, 7. And then again, I'll show you what that's going to be here in a moment. In the case of continuous compound interest, that is going to be that different formula with Euler's number in it. And so that is going to be our principal amount, which is 11,000, times E, Euler's number, to the power of your interest rate, 0.06, times the amount of years you're giving this money to grow, okay? So in each one of these situations, we just went through and set it all up, and what I'd like to go ahead and do now is show you the screenshot of the calculator here, where I actually punched all this stuff in ahead of time just to save time in the video here. And you can see that we get these dollar amounts, right? So we get, again, keep in mind that these are all dollar amounts. So in terms of interpreting these in terms of dollar amounts, of course, we're going to have to take a look at this as, 44 cents, and maybe 6 cents. Actually, that would be 7 cents if we were to round it, and then 58 cents if we were to go ahead and interpret that in that way. But anyway, yeah, these are all be dollar amounts here, and this is the amount of money that we are going to be growing into from our original $11,000. So this is pretty good growth. But you'll notice here that these numbers are not really wildly off. It just kind of depends on how many times a year you're going to be compounding. That's the difference between each one of these. And so in this first one, we compounded quarterly, and then monthly, and then continuously. And you can see that these are not far off, but they're pretty darn big, okay? So again, being able to compound that interest and calculate that correctly is very, very important. So as the last example in this video, let's go ahead and do another one here. So it says, when you were born, your parents deposited $10,000. That's going to be your principal amount in a trust fund that pays 6.25% interest. And so as a decimal, that would be 0.0625. That's going to be your R value, okay? And we are compounded continuously, so we know we need the continuous compounding formula, which is P is equal to Euler's number to the power of rate times time. And then it says, how much money will you have earned on your 18th birthday? Well, if we started when you were born, then that means that that is 18 years, of course, that has passed by, so that means that T is going to be 18. And now we have everything that we need here to plug into our formula and actually figure out what the answer is going to be. So our principal amount was, of course, $10,000. We're going to multiply that times Euler's number, E, to the power of your interest rate, which was 0.0625, we said, times the number of years you're giving this to grow on your 18th birthday. 18 years will have passed. Let's go ahead and demonstrate how we would type that in the calculator, right? So we're going to type in our 10,000. And then we're going to multiply this times Euler's number to the power of your interest rate times time. And again, we talked about this before, but in order to pull up Euler's number here, E, we're going to press second and then LN, which is that button that's right next to 4. That'll instantly pop up with E to the power of something. And we just want to go ahead and type in 0.0625 times the number of years we're giving this to grow, which it's our 18th birthday, so that's 18. And so if we punch that in, it looks like our money is going to be an amount that is over triple of what we originally started with. So we end up with $30,802.17 if we were to go ahead and round that, right? So let's write that down here. So $30,802.17. That is what our amount of money grows into, which is absolutely huge, okay? So again, the number of times we compounded in a year would be infinite in the case of a continuous compounded interest formula problem, okay? So anyway, that's all I have for this video. Thank you very much for your attention. If you guys have any questions whatsoever, then please, as always, feel free to let me know. But that's all I have for this one. So thank you very much, and I will speak to you guys in the next one.